The next lesson is over accuracy and precision. Okay, significant digits was the last topic that we discussed, and accuracy and precision is the whole reason that significant digits even exists. Okay, the significant digits is a way that we standardize how things are measured and how our answers are reported. And the reason that we have to do that standardizing is so that we can always make sure that our results are both accurate and precise. And so let's go ahead and define accuracy and precision so that we can further explain the relation to significant digits. Accuracy is how close a value is to the true or accepted value. And precision is how close a value is to a set of data. So in accuracy, where we have a true or accepted value, we're saying that we as the scientific community, after doing a bunch of experiments and getting the same results over and over and over again, we have all decided that that will be the true or accepted value. So for example, the density of water. The accepted value for that is 1 gram per milliliter. Okay, no matter where you go on Earth, that's the density of water, the accepted value. So if you are doing an experiment measuring the density of water for yourself, and you were getting values that weren't 1 gram per milliliter, then you would be able to say that you're not getting close to the accepted value. Now, as far as significant digits are concerned, it's really 1.00 grams per milliliter. So we have 3 significant digits in our accepted value. That way, when you're doing your experiment, if you come up with 1.02 grams per milliliter, for example, you were good on your measurement for the first and the second significant digit. It's just that the third one is where you lost accuracy. Okay, so the accuracy and precision and the sig figs really do tie into each other, and the whole purpose of having significant digits is so that we can make sure we're maintaining our accuracy. So whatever measuring device you were using that was great for the first sig fig and great for the second one, it faltered on that third one. So you would need to, if it was important for you to be significant out to the hundredths place, you need to get a different measuring device or fix the one you've got. If you only need to be accurate to the tenths place, then your current measuring device is good enough and you don't need to change anything at all, even though it's not good in the hundredths place. Alright, now let's talk about precision, how close a value is to a set of data. Okay, so let's pretend that a student, Mike, and another student, Allison, are both performing an experiment. They are going to go ahead and get the density of water. So I'll put up here what our accepted value for the density of water is again. Alright, and this time I'll include 3 sig figs. Okay, so they go in there, they have to get a certain amount of water, and then they're going to take the mass of that water, take the volume of the water, and divide, because we know that density is equal to mass divided by volume. Alright, so let's say that Mike does this, and his first trial gives him a density of water of 1.01 grams per milliliter. And then he does the trial again with a new mass and a new volume of water, and he gets 1.00 grams per milliliter. And then he does it again, and he gets 0.980 grams per milliliter. Okay, and then Allison performs this experiment, and she gets 0.68 grams per milliliter, and then 2.03 grams per milliliter, and then finally 1.53 grams per milliliter. Okay, well, let's just talk about the precision part of this data first. Let's go look at Mike's data again. If you'll notice, he's got 1.011 and 0.980. All three of those trials are very close to each other. Okay? 1.01 is really close to 1. And 1 and 1.01 are really close to 0.98. Okay, so all three of his sets of data are extremely close to each other. That means that Mike was very precise when he did his experiment. Alright, now let's go ahead and look at the data that Allison got. Okay, her data, 0.68 is nowhere near 2.03. Alright, that is way far apart. And 2.03 is not close to 1.53. And 1.53 is certainly not close to 0.68. So none of her data is precise. Alright. Now let's look at the accuracy aspect of their data. Remember that the density of water, the accepted or true value, is 1 gram per milliliter. Now look at Mike's data. It is all very close to 1. In fact, this one is right on it. That one is accurate up to the 10th place, and it only faltered in the 100th place, so that's really close. And then 0.980 is extremely close to 1. Alright, so these results over here are accurate, or are very close to being accurate. Now if you look at Allison's results, none of her information is accurate because all of her values are extremely far away from 1 gram per milliliter. Oftentimes when we talk about accuracy and precision in science, we get the bullseye example, so I'll go ahead and continue with that tradition. The first thing, let's go ahead and say that this first bullseye, and I'll number these so you know which ones I'm talking about. The first bullseye, let's say that a person shoots at the target, which is the center of the bullseye, and we'll say that that's the most accurate position, is the center of the bullseye. That's where you want it to hit. So they shoot at the bullseye and they get close to the center every single time, but all of their shots are spread out from each other. So in this case, we can say that they were accurate because they got close to the center every time, but they were not precise because none of their shots were close to each other. And remember, precision is about having all of your data being close to each other, and accurate is about having all of your data close to the accepted value. Alright, now let's say that this middle one, they shoot and all of their shots make it into the bullseye, and all of their shots are very close to each other. So in this case, they were both accurate and they were precise. Alright, now over here, let's say that they shot at the target and all of their data is really close to each other, but none of it is even remotely close to the bullseye. So here, they were not accurate, but they were precise. Okay, so those are your three possible outcomes. Now let's talk about bias. Okay, bias is anything that causes the data to be swayed or be less accurate, be further away from the true or accepted value. Okay, so what you're looking at right now is a triple beam balance. And on a triple beam balance, we have two lines. You have a line over here, and you have a line here. And this is the zero line. So those two lines have to match each other before you ever put anything over on the measurement tray. Okay, so notice that it is empty over here. Now what if the two zero marks did not match up before you put something on the tray? Let's say the tray is empty, but your zero mark is actually down here, like this piece right here is down at this level. Okay, so what that's showing is that there is less than no mass on the tray. Alright, so this is going to make any measurement that you take from this triple beam balance appear lighter than it actually is. And that introduces bias into your results. It causes them to be less accurate, you know, or the tray could start out at this level, and that would show that there is mass on it even though there isn't. So all of your results would appear to have more mass than they actually do. Let's go back and look at Allison's results for a second. If we look at Allison's results, remember she was not accurate or precise. Her information, her data is all over the place. There is a reason for that. Okay, so when Allison writes up her report over her experiment, she needs to give some possible reasons on why her data is nowhere close to each other. She needs to say something about either the triple beam balance maybe didn't start out at 0 like it should have, or maybe her graduated cylinder had soap residue left in it, and because of that it disturbed the surface tension of the water, and so it messed up her reading in that way. So looking at this graduated cylinder on the left, you can see that the water forms this concave shape, and concave means a shape like this. Alright, so water does that. That's one of the properties of water, and it happens because of some forces that we'll talk about later on in the course. But when you read on a graduated cylinder, you read from the bottom, which is called the meniscus. Okay, that's the correct way to read the level of liquid in the graduated cylinder. Now if you look over here at this graduated cylinder on the right that's got soap residue in it, you'll notice that the water, or whatever liquid that is in there, is not making that convex shape. It's just a straight line. That's because the soap has disrupted the surface tension of the water so that it can't do that. Alright, and so the results that you read from this graduated cylinder will be wrong. The water level is actually supposed to be at a different reading. That whatever results you get from that graduated cylinder will be incorrect. So that's bias in the graduated cylinder reading. And you can have bias introduced into any measurement you take, from a beaker, a burette, a graduated cylinder, a triple beam balance, a scale, anything, a meter stick. There can be bias in there for some reason or another. So it's your job as a good science student to look for these kinds of things, try and avoid them if you can, and if you can't, include them in your lab write-ups so that you can justify why your results weren't accurate or weren't precise. Alright, we'll leave it there for today. Thank you for learning with me, and I will see you next time.